we need to fix or modify in some way Ampere's law so that when we take our path integral along the curve, again seen here as an edge-on view, so we have our curve, and initially we've had this surface. So this surface is there, the curve edge-on is there. But here we can say that we would get I through due to the current going through to the capacitor. But if we blow this surface outwards into a bit of a bubble, which should be valid, that becomes this surface here, no longer does current actually go through that surface. So how we can actually fix that is to use electric flux. Now, the book does the mathematical derivation of this. I'm going to kind of describe it conceptually. So basically, we know that we have current in our wire, and the current is leading to a change in charge on our parallel plate capacitor. Now, if our charge is changing on our parallel plate capacitor, then the electric field is changing in our parallel plate capacitor. If the electric field is changing, then our flux is changing. And for this scenario, what we can basically do is say that there's some distance here, and keep in mind that we're looking kind of edge on. So we're looking at some area A. We'll assume that our electric field is uniform over that. So when you multiply that by E, whatever your electric field is, you get the flux. Now we use a little subscript of E here because we're about to start talking about equations that have both the electric flux and the magnetic flux in it. So our electric field depends on charge, and we see that the charge is changing due to the current. The area stays the same. So what we basically get then is that our time derivative of the electric flux is 1 over epsilon naught, where epsilon naught comes from the relationship between charge and electric field, dq dt, where this is just the current, right? So this here is the current, and notice that that would be the current through S1. And so in this case, area doesn't appear because area was also part of our electric field equation, and it's part of our flux. So that's why the area doesn't appear in this version. So effectively what we've said is that we have this path integral here. If we move our surface to be in between the parallel plate capacitor, we no longer have a current through, but we see that what we do have is a time derivative of the electric flux, and that actually does relate to the current coming in. So the reason we're talking about this is to try to fix Ampere's law so that the left side is always equal to the right side no matter what surface we draw that has the same curve on its end. Now, the name displacement current is a little misleading. There is no current here. We have an electric field, we have an electric flux, and our electric flux is changing in time. But there is no current here. And remember that current is the flow of charge. We don't have positive charges jumping over here. So when we call this displacement current, that's just historic. You don't need to worry too much about, the argument for why it's called that. I think it's a little confusing. But displacement current is a historic name. What we're actually talking about is the time derivative of the electric flux. So the displacement current, again, historic name, is going to be equal to epsilon naught multiplied by the time derivative of our electric flux. And notice that here we had dq dt times 1 over epsilon naught. So if you just rearrange this, you get dq dt equals epsilon naught times d phi dt. So that's what we're doing here. We see that this has the units equivalent to a current. And in fact, this is going to be equal in value to the current flowing into the parallel plate capacitor. But again, this isn't truly a current. It is not a current because no charge is actually jumping from one plate to the other. So again, this is not a current, or at least it's not a real current. So naming conventions are confusing. But what this does for us is that before we showed that if we just thought about this term, that we didn't actually get the same value on the right depending on what surface you get. Now you get this new term, the displacement current. So what I would encourage you to do is think about the equation actually this way, that our magnetic field path integral over some curve is equal to mu naught multiplied by two quantities here. One is current through, so this is the original ampere part. And then what Maxwell did was added this term. So this is the time derivative of the flux through whatever surface or through whatever curve is also defined here. So again, knowing that this is the displacement current is helpful, but again, it's not a real current, so that's why I'd encourage you to just think about it in these terms.